Currently, I wouldn't say we're doing a great job. I think the chemists hate us.
You're listening to The Cosmic Cast. Hello, and welcome back to another episode of The Cosmic Cast. We've been away from your screens for a couple of weeks, but we're back now. I'm John Pernay-Fisher, and I've got the regular co-hosts of Elliot Carter and Marissa Lowe.
Hello.
And we've got a very special guest this week, all the way from Cambridge, is Craig Walton. How's it going?
Hi, great. Good to be here.
Absolutely. Well, good to have you. So, so you're based at the University of Cambridge in your third year of your PhD now, and you've just had, very excitingly, a really cool paper out on a meteorite called Chelyabinsk, which is, I guess, this was your sort of first foray into planetary science, I guess. So I guess just to backtrack a little bit, so you're really interested in phosphorus, aren't you? That's sort of your main thing. So maybe I guess we could kick off by sort of touching on why phosphorus is such an exciting and important element to understand in a variety of contexts.
Sure. Yeah, I'm glad we start with phosphorus. I'm kind of being pigeonholed at this point, just because everything I seem to do always ends up back at phosphorus for whatever reason. But I mean, the main reason phosphorus is such an exciting element to me is that it's one of the main limiting nutrients for life on Earth and potentially in the universe as a whole. It's not present in the atmosphere. It has to come out of rocks, and it's quite rare in natural environments. So usually if you add more phosphorus to an environment, you're going to increase the productivity of that environment, more life forms kicking around. So if you can understand like the geological controls on the availability of phosphorus over time, the minerals that have been hosting it, their solubility due to the composition of waters at the Earth's surface over time, then maybe you can understand something about what's rate limited evolution and the evolution of the planet as a whole. And yeah, all the things that influence that. You've got phosphorus chemistry in meteorites and what set the composition of phosphorus in the planet when it first formed. So you can really take like different levels of planetary science, all from this one element, and connect it to lots of different things. So that's why I think it's one of the coolest elements. Yeah. That's my pitch.
Yeah, no, that's really
anyway.
Cool. Yeah, so John mentioned that you're looking at the Chelyabinsk meteorite. So I guess this was probably, I remember seeing the footage of this 10 years ago now, and I'm sure many people listening to it have. Would you mind giving us a bit of background?
Yeah, so transition from phosphorus to whole, phosphorus and Chelyabinsk, but Chelyabinsk is a really cool meteorite to work on because people actually have heard of it oftentimes, as you say, because it came in really unexpectedly in 2013 and exploded, air blast, above the town of Chelyabinsk in Russia. And in Russia, they have lots of issues with crime on the roads, so everybody has dash cams on their cars. So it ended up because it happened to be in that area, being one of the best recorded meteorite falls of all time, filmed from every angle, all the problems it caused. I mean, nobody was really seriously hurt, so I can kind of geek out about that event, feeling too worried about it. But it did explode in the air and smash a lot of windows. So it's really dramatic footage that you can show people the power of meteorites coming in. But then, yeah, filmed everywhere. People went out and gathered all the samples and sent around the world. And it just became this big news story. Everyone wanted to work on it. And so there's loads of papers and loads of data. So it's just a nice, well understood, well, maybe not completely, but reasonably well studied sample to work on.
Yeah,
it's cool.
It's an ordinary chondrite, isn't it, I believe?
Yeah, it's LL5, which means very low in iron. Yeah. The 5 means that it's been heated up quite a lot early in solar system history. Yeah. LL5, ordinary chondrite. Yeah.
I guess considering how many ordinary chondrites are out there and that have been collected so far, it's really cool that there's still some interesting and really science to be extracted from these actually, I guess, are quite fairly common meteorite types.
Yeah, so I mean, I guess there's just a lot we don't know about meteorites, even though, I mean, common when you're trying to sample the whole asteroid belt, understand what happened is still, relative terms. But I mean, the thing about Chelyabinsk is it is an unusual ordinary chondrite. I think the enthusiasm would have died down after a few years if it hadn't been quite strange, but it happens to be highly shocked. And it's a monomict breccia, which means all the material that forms this breccia came from the same place, but it's all been heated to different extents. So it has 3 different mythologies that make it up, all intermingled, all at different shock levels. So you can get insight into different parts of the cratering process just with this one tiny piece of rock, which is quite cool. And it's not so many shock meteorites, so it's quite nice.
I guess the obvious question then is how did you come to be studying phosphorus in Chelyabinsk?
Phosphorus in Chelyabinsk, yeah. So I was asked to give a poster presentation in undergrad, third year. I did a 5-year degree at University of St Andrews. And it could be on anything, just my first scientific poster. We just had to put one together for a class. And I randomly read a paper about shocked meteorites, this one in particular called Novato, which seemed quite interesting to me. So I did a poster on it. And then one of the lecturers, I went and pestered them to come look at it. They thought I did a pretty good job explaining the paper. And then randomly that same week, someone from the Open University down in Milton Keynes was visiting, who needed to fill a Paneth Trust position, which is an undergraduate-based mentoring scheme, essentially for 6 weeks, research institution. And so the guy that I give the post presentation to said, hey, maybe this guy Craig, he seems pretty interested in this kind of stuff. He does quite well in his grades. Why don't you take him down? And yeah, Mahesh and professor now, did that, and he's been a great mentor to me ever since. So I went down to the OU. The project I was meant to do with him on phosphates in a different meteorite class wasn't going very well because we couldn't find any phosphates in them. And so I was pointed to this other sample called Chelyabinsk, which people have reported phosphates in by a different mentor down there. And because I'd read this paper on Novato, I spotted some links between them. They're both highly shocked meteorites. And I thought, oh, maybe I can fill in some blanks here while I'm waiting for other samples, which never materialized. And that became a project, luckily.
That's it. Yeah. Well, yes, we were chatting a bit about this before we started recording, but it's amazing just how these small random events can just line up to result in some really cool stuff.
It was super exciting, to be honest, because I didn't have necessarily a lot of confidence, like going into it, that I'd be able to do any new science, or like, I don't know, I didn't expect to be able to do very much. But then just you get a few like random lucky things where you feel, oh, I know something about this. Oh, I can see a connection here. And then that's all science is really, is making connections between things that don't immediately seem related. So you get a bit of a sense of it.
Yeah, it's like, a bit like join the dots, really.
Whenever I talk to my parents about this, that's what we always say. It's just going to be good at joining dots. Yeah, that's what you're going to do. Yeah.
That's really cool.
Is that Paneth Trust scheme like still running or anything? Like, is that still available for undergrads?
It is. I'm not entirely sure what's happened during the pandemic, but it's definitely still going. It's a long running thing.
Yeah, we can put a link in the episode description if anyone wants to check out the website to see exactly what's happening for next summer, I guess. Or
yeah, I mean, my only advice to undergrads is that, like, I mean, I got really lucky. I wouldn't rely on luck completely. But essentially just talking to your lecturers about the things you're interested in, they'll tend to be able to point you in the right direction. I didn't really realize that was how it worked. Like if I'd just gone to Sami, who's the guy that ended up putting me in touch with Mahesh, and sort of told him I was interested in meteorites, he probably could have done that without it having to be this random thing. It can be engineered. It can happen.
Sounds good.
Yeah, so you said you've ended up looking at a couple of different shocked meteorites. So what is shock? What happens to the meteorite to make it be shocked? And how does that affect the sample?
So the reason shocked meteorites are really interesting is because that is the product of high temperature and pressure conditions induced during a collision. So you have two asteroids that smack into one another. The material at the epicenter is going to get heated up really high temperature, potentially melted, squeezed to really high pressures, which will induce mineral transformations potentially to high pressure analogs of the minerals that were there. And the most like big picture interesting thing about shocked meteorites, apart from just like the intricacies of like mineral physics and weird stuff that we might care about, is that it's telling you something about the state of the solar system at large. So actually that was the reason I presented that poster way back in third year, is because it's a paper that was trying to relate the timing of collisions between different asteroids to major events in the history of the solar system. So they were saying in this paper, and saying I'm still really interested in trying to prove or disprove, that you have the collision, like the biggest type of collision you can imagine, between the proto-moon and the proto-Earth. And this sends out material into the solar system, which can then collide with asteroids in the main belt. And then the meteorites that we sample, if they're all from the similar time, that could be a record of that event. So it could be this indirect record of moon formation. And I just thought that was like a pretty mind-blowing concept. But it wasn't necessarily, it was a big paper in Science by William Botke and his co-authors. Really cool. But there was just loads of questions that remain about, are we actually like measuring the ages of these collisions? Were the meteorites right? Is the modeling correct? So it's like a big, like unresolved thing, but like a super exciting concept. So I would say that's why shock meteorites are cool. They tell you about collisions at lots of different scales.
Yeah, that's crazy.
Shock, do you need to have a very high velocity impact?
No.
Oh, okay.
No, well, high. I mean, like you can get down to like a few kilometers a second, which is still fast. But like I think the average collision rate now is about 3. But it is interesting when you get into like these debates about what are the meteorites sampling from the asteroid belt, because in that paper they say that the average velocity of stuff that went into collisions from the material that gets ejected is more like 15, I think, or 12 or 15 kilometers a second, and the amount of material that gets shocked in that collision scales exponentially with the velocity. So I get that's where their whole prediction came from, that because the relative velocities were so high, perhaps like almost all the material in the asteroid belt should have been shocked in this single event, because the background collisions, they'll still melt stuff, but not very much. So that was kind of why their model predicts that even though we have this fairly random and bad sampling of the asteroid belt via meteorites, it could still show up this event more so than anything else. That was their whole prediction.
I guess sort of linking then this into, I guess, what you've been doing with phosphates. It's mostly apatite we're talking about here, isn't it, I suppose? Or is it parallite as well, maybe?
It's both of them. It's both of them. In the paper we're looking at both. Yeah.
So I guess you're using these minerals as proxies for understanding shock, I guess. Is that how it works, I guess?
Yeah. So I talked about phosphorus as a nutrient at the beginning. In the meteorite context, there's nothing to do with that because there's, as far as we know, no microbes on these asteroids. But yeah, you're exactly right. Phosphates are interesting because they're relatively ubiquitous, and they can respond in terms of their microtextures to shock in quite variable ways. And we've noticed that in terrestrial impact craters, and it's now beginning to be studied in the moon, a lot of settings. So you can use their chemistry, and in particular, they might be able to tell you when the impact happened, because they partition uranium. And when they form, which is the case to lead, you can measure the isotope ratio of the two. It's been a closed system and find out if it got reset at some point, if it got heated up and lost some of that lead. That gives you the age of that event, potentially a collision when you're talking about an asteroid. So phosphates are really nice in that regard. They're everywhere and they can tell you nice things about impacts.
What are some of the specific techniques you're using to study phosphates?
So, I mean, the thing that I use most of is simply SEM, using backscattered electron images, secondary electron images on the SEM to zoom in. It's kind of embarrassing. I've barely used an optical microscope during the PhD. I've got such good access to the SEM, and it's just so nice to be able to zoom in and get really lovely images of the phosphates. I've got very good at picking them out by eye in the grayscale images. So yeah, mostly SEM. That's what I've used way back at the OU. I just basically got left to work it out, put in the room with the SEM and find the phosphates. But then also things like electron backscatter diffraction, to find out the orientation of the crystals, whether or not they've been deformed, recrystallized. Yeah, those are the main things, SEMs and things you can plug into them.
So from all this, what were you able to find out about Chelyabinsk?
Quite a lot, I would say. I'm gonna think for a second about where I want to start with it. I mean, the main headline really from it was that the three different lithologies, I'll tell you what they are. So there's the light lithology, which just has a few shock melt veins going through it. Chelyabinsk also has a dark lithology, which has way more, and a melt lithology, which is basically just rapidly cooled, quenched melt. And we found the phosphates in each of these lithologies were very different in terms of their microtextures, rather than being the same. So in the light lithology, they show a reasonable amount of crystalloplastic deformation of the lattice. In the dark lithology, they've been recrystallized and they're like beautifully pristine. And then in the melt lithology, there are no phosphates. They're all gone. They've all been destroyed, and the phosphorus is instead in olivine. So I guess that's like for anybody working on shock, that's kind of like the cool thing. Because maybe you can test some hypotheses. We can talk about that a bit about when the impact happened, because they are showing a different response. Maybe they should show different ages depending on when the impact happened or not. So that was kind of the main thing that I'm going to be continuing to drive forwards. But there was some other stuff. It's a long paper.
That's cool though. So I guess so you got a bunch of different lithologies that are all sort of shocked in slightly different ways. I guess it really sort of shows what a hodgepodge some of these samples can be, really.
Yeah, no, you're absolutely right, and that's what makes them quite difficult to understand. I mean, like the thing with Chelyabinsk, I guess one of the reasons that I was drawn to it when I was reading about it is that people still don't agree when this impact happened. That shocked and produced all this complexity. There's a paper by Kevin Reiter, which lists about 12 different possible ages, and they span like literally all 4.5 billion years of solar system history, using different techniques in what you study. And the thing that jumped out to me was that the phosphates, this is like my personal opinion at this point, but the phosphates are the only things that show consistent ages in different shock meteorites. And I mean, doesn't necessarily have to be the case, but it is interesting to me that in lots of shock meteorites, the phosphates give you similar ages. So to me, that's like, that's interesting to investigate. Maybe we should try and understand specifically what the phosphates can tell us.
There's the uranium-lead.
The uranium-lead ages, yeah. There's lots of shared uranium-lead ages between shock meteorites at this point.
Yeah, well, that's interesting. I guess historically that often has been used to tie together single impact events, isn't it? So it's quite interesting. But I guess, I mean, how much material were you working with in the first place? I mean, how much does like sampling bias affect how much you can really say about these?
From a single meteorite, you mean? So I had a thin section of each lithology, and then I guess, people have done loads of work on Chelyabinsk, so you can contextualize your samples within the other stuff and make sure there's nothing anomalous going on. So it's pretty well characterized at this point. But yeah, I only had the 3 thin sections. So that's what I had. It's difficult to get much more. I mean, you could do like it's nice that the Russian government handed out as much as they did, to be honest, for people to just use and do whatever they wanted with. But meteorites, I guess they're pretty, they're finite. Even ordinary chondrites, individual samples, you can't just go around destroying loads of it. But yeah, I had three sections.
Yeah, do you know how much they recovered in total?
I think it was at least a few kilograms. I think it was quite a lot, relatively speaking, which is another reason why it was so good, because everybody in the world was, not everyone in the world, lots of labs were given something to work on.
Because
I think cool.
Didn't it fall? It was in the winter time, wasn't it? So didn't a lot of it fall in like snow and stuff to really sort of help preserve how fresh it was and things like that?
I think you're right, and I think a bunch of it fell in a lake as well.
Yeah, that's right. Yeah,
a main big piece fell in the lake. I mean, we've got some experience here in the UK now of the excitement of meteorites falling, because we had one just a month ago.
Indeed. We'll put a card to me chatted to Ashley King.
Yeah.
Wants to find more about that.
Yeah, I mean, I was emailing Ashley, being like, oh, can I join in? If there's never another meteorite hunt. He did an amazing job in recovering pieces of that. But yeah, I mean, when meteorites fall, it's super exciting, especially if they're a cool sample.
Absolutely. And I think this is a good example, really, of just how much science we can get when one of these impact events does occur. I mean, they're hugely important for meteorite scientists, really, I suppose.
It engages people. Because, you know, when you want to engage someone from the public about this, you know, you'd be like, have you heard of the Chelyabinsk meteorite? And they'll be like, maybe not. And you're like, it was recording all the dash cam footage and it was on the BBC News. And they'll be like, yes. And then suddenly they're just interested to find out about my wacky stuff that I could use the meteorite for. It being an event definitely helps.
Yeah, for sure. Yeah. Cool. So I guess a lot of this phosphate work has now been published in Maps, isn't it? I think.
Yeah.
So that's one of the meteorite journals that we like to publish in. So we'll put a link to that paper in the episode description if anyone wants to read a bit more about it. But you mentioned before we started recording, then you might be doing some more analyses on these samples, and you might be doing a bit more.
Yeah. So there's a bit of a story. I wanted to do a lot more uranium lead analyses using SIMS, so secondary ionization mass spec, just state of the art for getting spatially resolved uranium lead ages and phosphates at the moment. And that's quite an expensive, difficult thing to do. There's not a whole lot of SIMs that do the stuff well. So I've been on a bit of a wild goose chase, like trying to find a lab that actually wanted to do it. So essentially I wanted to see if there was any correlation between the different populations of phosphates and their ages. To see, you know, whatever. We tried here in the UK. I won't say too much about that because that didn't go very well. But then we ended up going to Stockholm, to the NordSim with Martin Whitehouse, who's brilliant. But the Stockholm instrument had some issues. So the delay of like a few months with NERC turned into a delay of like a year. Not to say anything bad about NordSim.
Well, their SIMS has been down for most of last year. Yeah,
exactly. So that was just what it was. And then the pandemic happened, and I ended up having to, you know, talk to Mahesh and be like, look, I really think we can get like a follow-up paper to this. It could be pretty high impact, no pun intended. If we got the uranium lead data, I wanted to get it for the PhD is over. And he put me in touch with some collaborators in Beijing at the geophysical lab over there. Sen Hu, that's the guy. We sent the samples over. There was a lot of drama at the Chinese customs. I was sitting where I am right now, freaking out for about 2 weeks that my precious samples that I've been working on for like 4 years were never going to see the light of day again because they got impounded at the border.
Blimey. How come?
Because I had given a phone number. You have to provide a phone number for the recipient. The phone number I gave was for like Sen's desk in his office. And it was the pandemic, so he wasn't there.
Yeah.
Oh, God.
That's stressful. Yeah, that sounds pretty stressful.
So they just were like, oh, this is not whatever. Like, led to a big drama. Eventually managed to give the Chinese customs his mobile number.
Okay.
And the samples got there. And he was a star and did the analysis in 2 weeks.
Wow.
Rather than like 2 years. And the data is pretty cool. The other point I would make before, I don't know, it's just about olivine. Because it's in the title of the paper is phosphorus olivine assemblages. We got some, sure that's some olivine right there, right? Behind you.
Oh yeah.
Yeah. So one of the weird things, less related to the whole shock story, is that the phosphates in Chelyabinsk are like exclusively intergrown or with olivine grains. It's really weird. And it's just strange because like from a first principles, you'd be like, well, what the hell is in olivine that would make phosphates? But it really does seem that these phosphates, you know, they grew and replaced the olivine grains. So they're full of these olivine inclusions, which all have the same, you know, crystallographic orientation. So it really seems like there was an olivine crystal there, and now there's a phosphate. And one of the things we come up with in the paper is pointing out that in some of the less metamorphosed chondrites, you find phosphorus-rich olivine crystals. It's super weird. I mean, have you heard of phosphorin olivines? Like no. Yeah, you can find in certain conditions phosphorus-rich olivine crystals, usually high temperature, like in Chelyabinsk in the melt phase. But we sort of spin this story towards the end of the paper where we say, well, potentially in all of these chondrites, you have phosphorus in iron metal at the beginning when the thing first forms. Then it begins to get aqueously and thermally metamorphosed. You oxidize phosphorus out of the metal and you form phosphorin olivine. I don't really understand necessarily why, but that is like observed to be in these like intermediately altered samples. And then that maybe is the reason why the phosphates end up forming centered on the olivine, which I just think is pretty weird.
That is weird.
But it's cool. Yeah,
it's completely incompatible in olivine.
Well, it's not. Well, it's not
Very low in
completely. It's relatively incompatible, but it's not completely.
Yeah.
So when you say phosphorus rich, how much are we talking here?
It's like it's more like 0.15 weight percent.
Okay.
I think, which is still pretty high. But you can get phosphorin olivines, which are like very high, but they tend to be like a bit weird. Like you're rapidly cooling a melt. The phosphorus is incompatible in everything that's growing, and then you end up with this really phosphorus-rich liquid at the end.
Yeah.
So it has to go somewhere.
Yeah.
Is it like a lack of calcium or something to make apatite, and then it just has nowhere else to go?
I guess so. It's super strange.
Yeah.
But yeah, it's really weird. The reactions are like,
yeah,
I don't know.
Cool. So I guess bringing it back down to Earth then, I suppose the link here, I guess, is that you've got these phosphorus-rich meteorites and phosphorus-rich primitive materials, and that's then being delivered to the Earth. And I guess is that what's giving us all this phosphorus on the Earth that then life can exploit, do you think?
Well, initially, certainly when the Earth was formed, that's how it works. I mean, I guess, so that's sort of a nice segue to like some of the other things I'm interested in, which is the origin of life. And life afterwards.
Just that.
It's a really cool topic that I just ended up reading about back in the day when I was starting a PhD, because phosphorus is so critical to that topic. It's basically just really hard to get enough. Like in the lab, when people are trying to make RNA, phosphorus is in all these different biomolecules. When they're trying to do it, they need really high concentrations of phosphate in their experiments. And there's not many places on Earth in water where you find high phosphate concentrations. So the question really becomes like, is that right? Is it some like weird way that's possible? Or do you need like a really soluble form of phosphorus that was only around at the time? And meteorites are one option, because some of them are full of iron, which still has the phosphorus in it. It's in a reduced oxidation state, and then that's super soluble in the water. So some of my collaborators in Florida, Matthew Pasek, he's the big boy on this, and that's his whole thing: meteorites bringing phosphorus down. And I've got a few papers submitted on that. I don't know what happened to them, where we sort of consider a few other options. I'm not even sure if there are really solutions to the problem, and the problem is that apatite, which we talked about in the meteorites, is also the main host of phosphorus at the Earth's surface today. But it's not very soluble. So people are always worrying about, can we make apatite soluble, get the phosphorus in the water for the origin of life? They come up with all sorts of different solutions to that. But one of the main issues of this whole paradigm is, what if, rocks 4.5 billion years ago aren't full of apatite? If you have no continental crust and you just have some basalt that formed at high melting temperature, or komatiite, there is no apatite to speak of most of the time. And instead, the phosphorus is in our friend olivine, despite the fact that it's incompatible. And so that just changes the ballgame completely. So yeah, we made this argument that maybe people are looking at the wrong phase entirely. And it's really not, I'm not convinced that it's the solution to the problem at all. I think it might make it more difficult. Because with apatite, I mean, don't drink too much Coca-Cola because you'll dissolve your teeth. Apatite's more soluble at low pH. There's ways you can think around it. With olivine, it does become a bit more like, how are we going to get enough out? So
it doesn't help. We've only got a handful of representation of mythologies that were present in those days, I guess.
Oh yeah, definitely. It's a big problem. I guess the point of that paper, we're just trying to argue that people are very like blindly focused, assuming that they know what it was like. We don't really, and saying that it was definitely apatite. Maybe there was almost none during the time window when life was evolving, which now seems more likely to have been like almost immediately, rather than after like 1 billion years.
So how does that time with sort of the black smoker type hypotheses then, when you got these big hydrothermal events underwater? Does that help the case for apatite and phosphorus, or?
A good question. Yeah, so the whole like where did life happen thing is like really hot stuff at the moment. There's been a bit of a transition in the leading ideas. So yeah, there's the deep sea vents idea, which I would argue like has real trouble with this kind of stuff, because any phosphorus, I mean, so they say you've got on a black smoker, it's acidic, and then the fluids are dissolving some apatite, which happens to be there for some reason. That phosphorus is just going to be lost to the ocean and be diluted. So perhaps a more useful setting would be the same thing, but subaerially on land in some restricted pond, where you still have the hydrothermal activity. It's still acidic, it's dissolving out some phosphorus, but it can build up.
It's a closed environment, I guess.
It's a closed environment, exactly. So there's been a lot of exciting work about that.
Yeah,
recently.
and I guess then I suppose you've got the problem that there wasn't much continental crust and land about to do this in the first place. That sort of a chicken and egg situation, isn't it? Really? Yeah.
All of stuff in Origin of Life is challenging because of that exact stuff. Like life relies on these complicated relationships between RNA and enzymes, proteins, which you need one to make the other. You need the DNA to print to make the enzyme, and the enzyme to make the DNA. So yeah, these paradoxes are like all the way through that topic, which makes it really cool. And I just like the idea that it's an earth science problem, even though it's a biology thing. Yeah. So maybe earth science can constrain it somehow. Currently, I wouldn't say we're doing a great job. I think the chemists hate us, genuinely, because all we do is like change our minds. Like 20 years later, we're like, actually, don't know, composition of the atmosphere might be totally different. Sorry, guys. So like, and they have to listen to us because they don't. I mean, I went to one Origin of Life conference a few years ago, and I became known as Mineral Man. Because there's just no geologists, or not very many, thinking about this. So like, if you know anything about minerals, suddenly you're like the authority. Which did lead to me writing the other paper, the PhD, is more a big review paper where we just comment on like which minerals are involving phosphorus may have been there at the start or not, because you can actually rule out like almost all of these things.
I guess that really sort of highlights the importance of intercollaboration between disciplines, then, doesn't it? Really try and solve these really top level questions.
I completely agree, and in fact, I feel like it's not like formalized enough in Origin of Life science. It does tend to be this like informal thing where the chemists are doing amazing stuff, and occasionally they'll ask the geologists like, "Is this at all reasonable?" They don't really feel that it's like intrinsic to what they're doing. And similarly, I wouldn't say there's very many geologists that feel that the Origin of Life is an earth science problem. Has to be. So there's like droves of us doing it. So we did write a preprint, trying to like come up with a concept that might appeal to people and bring everyone together, called interference chemistry. It's on Chem Archive. You can go and read it. The whole concept being that if you have a system of reactions that could lead to life, you're going to have things in the environment that are going to interfere with those like lab-based experiments if they were in reality, either positively or negatively. So, but you're not going to know what it's going to do until you try. So it's like impossible to guess. Like the chemists want to like plan it all out beforehand because it's what they're used to doing, carefully designing an experiment. But nature is messy, and whatever happened to make the Origin of Life must have been messy. So my argument is that they should take their best guess and then like subject it to the actual conditions of submarine hydrothermal vent, all the bells and whistles, everything that would have been there, and then see what happens, and then like subtract and add things to work out why their experiment might change. I just think stochastic outcomes would be really useful, and just always them trying to guess and then me telling them whether or not their guess is like reasonable. It just seems pretty inefficient. So that's kind of the idea, but I don't know. We find it difficult to get it published so far, to be honest. we had one unnamed journal who rejected it after a while, who just said they didn't think geology would ever be well enough understood to be useful in this context.
Excellent.
And I was like, well, we'll give up then, because then we'll just know the answer. Fine. What? Oh, yeah. So, yeah, it's really and actually that rejection convinced me that the paper was like vaguely useful, because like if that's the opinion, then we need to change it.
Yeah, well, yeah, absolutely. Yeah. Interesting stuff. Yeah, well, that's absolutely fascinating. I guess we should probably start thinking about wrapping this episode up, though. That's the origin of Earth stuff is really, really cool.
On a journey.
Yeah, phosphorus from meteorites all the way down to Earth. So we've got one final question for you that we'd like to ask all our guests. Perhaps Marissa or Elliot, if you'd like to ask that final question.
Yeah, go for it, Elliot.
Yeah, sure. So if you could do anything aside from what it is you currently do, what would that be and why?
That's a good question. And I actually have the answer. Probably that doesn't reflect on how well my PhD is going. No, I would be a science fiction writer.
Phenomenal.
I love writing. It's what I wanted to do initially when I went to university, before I discovered that telling stories about real things maybe is also quite cool. But yeah, I've kept it up during everything. Like I've written a book. I don't know, might send it somewhere. My favorite author also did his undergrad at University of St Andrews, and he ended up like quitting science a few years into his postdoc because his book just blew up.
Who was that?
Alistair Reynolds.
Okay.
Really good. Check him out. I think I might stick in science if I can. I really do enjoy it. But yeah, writing is I had to unlearn writing to be able to do a paper.
Yeah, I can imagine very different styles there.
It's pretty heartbreaking. The first thing I wrote was just like way too long and like, a complete story. And then the supervisor was like, no. No.
Yeah. I understand, your reservations about, the style we write papers in. I sometimes wonder, is this the best way to communicate this information?
Yeah,
I have no idea.
It takes a long time sometimes to understand a paper and a long time to write it into that form.
Yeah.
I'm not completely convinced. I had this thought recently that everything should be like a nature paper. In that, like, you write the paper with all the information in the SI, and then you have the like short and sweet summary that everyone can understand. Like, why do we not just do that all the time? Maybe it's because no one would ever read the hardcore stuff. I don't know.
Yeah. It's an interesting point, though, because I've seen a few journals. I think it's the AGU journals where you have got a lay summary and then the abstract, and they're both of a similar length. And I just remember thinking just the other week, actually, like why even bother with an abstract? Because the lay summary is still giving you the same information and it's actually readable. So surely you're just, the two aren't compatible, surely.
Yeah.
I mean,
that I read the main audience one and I've no idea what the main abstract says.
Yeah, there's definitely a breakdown there somewhere, isn't there?
It does feel like a taboo thing to admit, though, right? But if I go more than like outside of my very immediate field, it'll take me a long time to read a paper from cover to cover.
Yeah, there's so much jargon and it's very dense. Yeah, I've seen a few articles about this recently, actually, with people talking about how particularly publicly funded science perhaps should be a little bit more accessible than it is in the way we publish this kind of stuff. So yeah.
Well, I know how hard it was to read my own paper. It doesn't bode well, so it's really tricky. I'm gonna try and keep it much shorter from now on, if possible.
Nature only.
Yeah, nature only.
Nature only.
Yeah, exactly.
Easy.
Cool, brilliant. Well, Craig, thanks very much for coming on. That's been a fantastic conversation. And if any of you in the audience would want to delve deeper into these topics, we'll put a link to a variety of some of your papers, Craig. And if anyone wants to find out a bit more about the Paneth internships, there'll be a link in the description where you can find out a bit more information about that as well. So yes, in the meantime, Craig, thanks once again. And to all you lot in the audience, we'll see you all very soon. If you want some more Earth and Solar System content, be sure to check out all our links to social media. They're on the screen right now and in the episode description. But until then, have a very good week and we'll see you next time. Bye.
Thanks very much. Bye.